Next, we're going to take a look at rotational motion. Rotational motion is about describing the motion of an object that is either spinning or an object that is moving in a circle. So with rotational motion, we want to describe this spinning motion with numbers that are valid for the entire object and don't depend on the distance we are from the center of that object. So take as an example this record. You know that a point on the label of the record, a point on the outer edge, is going to be traveling a smaller distance than the point on the outer edge of the record in the same amount of time. So the speed of a point of an object on the outer edge of the record is going to be traveling with a greater speed than a point on the label, but they're both rotating at the same rate. And it's that motion that we want to describe, where we have one number that describes the rotation and is the same for the entire object. So to do that, first let's look at radians. So radians is how we describe where on the object we are, and if we have this circular rotating object, a single radians measure can describe any point along a line drawn from the center out to the edge of the object. So radians are a way of measuring angles, and the angle in radians is equal to the arc length along the circle divided by the radius out to that point. So if we wanted to find this angle in radians, we could take this arc length and divide by the radius of the circle. So these radian angle measurements generally are measured from the positive x-axis in the counterclockwise direction. And here we have a table where we are making analogies between degrees and radians. So 0 degrees is the same thing as 0 radians. 360 degrees all the way around the circle is equivalent to 2 pi radians. 180 degrees is equal to pi radians. 90 degrees is the same as pi over 2. 45 is the same as pi over 4, and so on. Now I always get asked, do we have to memorize this table? And no, you don't need to memorize the table, but you should know one or two equivalent angles on the table. So either remember that 360 degrees is 2 pi, or 180 degrees is equal to pi, and that will allow you to convert from degrees to radians. Now, just a word of warning, the equations in this chapter use radians. We've been dealing primarily with degree angles up until now, but for the equations in this chapter, you need to use radians. So the first concept that we're going to look at, now that we understand how to measure angles in radians, is something called angular displacement. And angular displacement is the difference between final and initial angles. It's measured in radians, and if you have a rotating disc or wheel, then all of the points on that disc or wheel will go through the same angular displacement. So imagine we have a point here at some initial time. At some later time, as the wheel rotates, the point will be over here, and we'll have some new angle, theta final. So the difference between the final angle and the initial angle is the angular displacement. So that would be this angle along here. And all of the points on this wheel, whether they're close to the middle or further out to the edge, anywhere they are, they will go through the same angular displacement. They will turn around the center of the wheel by the same difference in angle. Now that we have that concept of angular displacement, we can also define angular speed. Angular speed tells us the rate of spin, how fast is an object going, or how fast is an object going around a circle. And the rate of spin, this angular speed, the average angular speed, is equal to the angular displacement in some time, just like regular speed is equal to a displacement divided by time. Now, sometimes you will see angular speeds expressed in rotations per minute, and if you do, then it's important to convert them to standard units of radians per second. one rotation being equivalent to 2 pi radians. Now we use the convention that if omega is positive, so this symbol is omega, if omega is positive, the angular speed is positive, then theta is increasing, so we have counterclockwise motion, and if it is negative, then theta is decreasing, meaning that we have clockwise motion. There is also an instantaneous angular speed, just like there's an instantaneous velocity, where we look at a very, very tiny amount of time and see what the angular displacement is in that very, very small amount of time in order to figure out how is the object spinning, what's the rate of spin at just that instant. So let's look at an example, and this example will help us to figure out what the angular speed is for something that's not given in radians per second. So we're told that in this case the grindstone is spinning at 8.3 revolutions per second, and we want to find the angular speed, which should be in radians per second. So we know that our angular speed, or what we want to be our angular speed, is 8.3 revolutions per second, and we want this quantity to be in radians per second. Well, we know that 1 revolution is equivalent to 2 pi radians, because 2 pi radians is once all the way around the circle. So if you undergo 1 complete revolution, you're going through 2 pi radians. So then that's going to be equal to 52.1 radians per second. And if we were told that we had some number of RPMs, well, RPMs is the same as revolutions per minute, and in that case, we would use the same strategy of changing revolutions to radians, and then we know that 1 minute is equivalent to 60 seconds. And so that's how we would go from revolutions per minute, or RPMs, to radians per second.